You know, there's this one number that has basically haunted physicists for more than 100 years. It's a number so fundamental to our reality that if you tweaked it just a tiny bit, stars wouldn't shine, atoms wouldn't hold together, and life, well, it just wouldn't exist. That number is 137. So what's the deal with this number? Let's dive in.
Okay, so to be super precise, it's the inverse of this value here, roughly 1 divided by 137. This is the fine structure constant, which physicists call alpha. The weird thing about it is that it's a pure dimensionless number. It doesn't have any units like meters or seconds, it just is. Basically, it's the master control knob for the electromagnetic force. It decides exactly how matter and light talk to each other.
I mean, even the great Richard Feynman was totally stumped by it. He called it, and this is a direct quote, one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. For decades, we've known how to measure it with incredible accuracy, but nobody has had a clue why it has this exact value. It feels almost arbitrary.
But here's a thought. What if it's not magic at all? What if we've been looking for the answer in all the wrong places? What if its origin is hiding in plain sight, not in some mystical formula, but in the actual shape of our universe?
Well, there's a new theory out there that suggests exactly that. It's called the harmonic scale framework, and it's offering a completely fresh and kind of radical perspective on this century-old puzzle.
So, the big idea behind the harmonic scale framework, or HSF for short, is to stop thinking about the universe as just a bunch of tiny, separate billiard balls bouncing around. Instead, picture it as a symphony of interconnected waves and resonances.
What this means, in the HSF model, is that particles like electrons aren't these little solid balls. Think of them more like standing resonances, like the pure vibration on a guitar string. And here's the kicker. All of these little vibrations, every particle, exist inside a shared universal boundary. A boundary that isn't a perfect sphere, but is actually a little bit flattened, like a slightly squashed beach ball, an oblate spheroid.
And here's where it gets really wild. This framework doesn't just describe things, it actually tries to calculate the value of alpha right from the ground up using these principles. So let's see how its first attempt stacks up.
So how do they do it? The HSF calculation kicks off with something physicists know inside and out, the ground state energy of a simple hydrogen atom. The theory builds a bridge, a direct link between this basic energy level and the electron's own inherent energy. And from that, it spits out a value for alpha.
And just look at the result. On the left, you've got the prediction from the HSF theory. On the right, the value we've actually measured in labs for years. I mean, look how close these are. We're talking about a difference of just 0.02%. That is wildly accurate for a first principles prediction.
But wait a second, it's not perfect, is it? And in the world of fundamental physics, a tiny difference can be a huge problem. So is this it? Is that tiny gap a deal breaker? Does it mean the whole theory is just a near miss?
Well, hang on. The folks behind this theory say not so fast. They claim that little gap isn't a failure, it's actually the key. The answer, they say, is written in the very shape of our universe.
Nope. That 0.02% is not a mistake. It's not a failure. According to this framework, it's a predicted geometric correction. It's supposed to be there. The difference is actually part of the prediction itself.
Okay, so here's how it works. Remember that slightly squashed beach ball shape of the universe? The theory says it has a specific flattening of about 2%, but a hydrogen atom at its most basic energy level is perfectly spherical, so it doesn't feel the universe's flattened shape directly. It only experiences that distortion as a tiny second-order echo, a really subtle effect.
So this is the big reveal. That 0.02% deviation we saw isn't a flaw in the math. According to the theory, it is the calculated size of that geometric effect. It's the signature of the universe's slightly flattened shape, literally imprinted onto this fundamental number.
If this holds up, it completely changes how we look at this number. It's not about magic anymore, it's just geometry.
The original paper puts it like this, saying 137 is the intrinsic K1-K2 coupling strength determined by the global spheroidal geometry. Okay, that sounds dense. So let's actually break down what that means in plain English.
All right, so in this picture, you've got an electron which has an internal mode, let's just call that matter, and it interacts with the electromagnetic mode, which is, light. The coupling strength alpha is just a measure of how efficiently energy moves between the two. It's how easily an electron can absorb or spin out a photon of light.
This just flips the whole mystery on its head, right? The traditional view says alpha is this fundamental, mysterious, magic number that we just have to accept. But the HSF view says, no, it's structural. It's derived from geometry. It's not magic. It's a stability ratio that's baked into the very architecture of our cosmos.
Okay, so let's just walk through the logic one more time, step by step. First, particles are modeled as hybrid structures. Second, you derive a baseline value from the energy of hydrogen. Third, you factor in the overall shape of the universe, that slightly squashed sphere. Fourth, you calculate the tiny correction that shape causes, and boom, you get a final result, a geometrically enforced ratio.
So the huge takeaway here is that 1 over 137 isn't just some random number the universe pulled out of a hat. The theory suggests it's a structural property as fundamental to our universe as the number pi is to a circle. Except in our case, the cosmic circle is a slightly squashed sphere.
And that, of course, leaves us with a mind-bending question to chew on. If the very geometry of the universe dictates a constant, this fundamental, the one that governs how light and matter interact, what other parts of our reality, what other laws of nature, are not laws at all, but just reflections of the universe's shape?